Hello everyone. In this lesson, we're going to talk about the number e and natural logarithms, branching off of our general topic of logarithms for the week. So we're going to talk about what is this number e, where does it come from, what is it equal to, how is it related to exponential functions, and then we're going to talk about this guy right here. We've seen this before, particularly in terms of population. So the population equals the initial population times the factor to the power of t. So in these notes, we will learn how the number e relates to exponential functions. We're going to solve some more equations. So we're going to solve for some unknown exponents using properties of natural logarithms. Also, this will probably be a nice review of some old algebra skills like factoring. And we're going to simplify natural logarithmic expressions. Okay, right here, convert this, what we've learned already, this initial point p sub 0 times a to the t to p sub 0 times e to the kt. This form is much more often used in mathematics and physics to represent tons of different things, but especially population and any sort of exponential growth often uses this number e. But we can convert between the two, and there's really not that much difference, and just this one is a much more popular form to use. And we're going to learn about that today. And like I already basically said, we're going to apply natural logs to represent population. All right, so some background. This number e, this is named after this guy named Euler, E-U-L-E-R, who is this Swiss mathematician in 1700s. He claims that this number represents the word exponential, like exponent, whatever that word is in the Swiss language. But some people think that he just named it after himself. I'll let you decide what you think there. Here's the number e, 2.718281828. Yeah, this whole thing. This is an irrational number, which means it cannot be represented by a simple fraction, which means this decimal goes on forever and ever. It's like pi. This e came to be because people kept finding this number in mathematics. It's a pattern number. It's just a pattern that's seen in lots of different places. So they said, okay, we need to name this thing. So they named it e. Just like pi is named pi. Let's see. Okay, last, e is the base of the natural logarithm, like ln, which were invented by this guy named John Napier, which is a Scottish mathematician in this era. All right, so where does e come from? How is it calculated? Two big ways. Okay, the value of 1 plus 1 over n to the n, if this looks familiar to you, like if you've taken any financial classes, this looks very similar to how you calculate compound interest. And this number is used in calculating compound interest, which is useful. So this is this function, 1 over 1 plus n to the n, or 1 over 1 plus x, 1 plus 1 over x to the x. As this goes forward, it approaches this asymptote of e. And this guy, okay, these are so cool. These are one of my favorite things about mathematics. We'll learn more. We'll discuss sequences and series in this class. It's kind of a hit or miss if it's taught in a calc class, but I would like to touch it, especially because of its roots in Indian calculus. So calculus that comes from India focused a lot on stuff like this, which isn't often taught because, we're in the western part of the world, so often we base our mathematics on like European roots, which is why we hear about this guy Euler, why we hear about this guy Napier, why we hear about Pythagoras, and why we don't hear about mathematicians from other cultures around the world who had these ideas actually much sooner than these European people. Anyways, okay, so the value of e is also equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. So this is just a pattern. You see the pattern here? Also, factorial means like, 4 factorial is 4 times 3 times 2 times 1. And if you add these up, this ends up equaling e. So this is one other way that it came to be. And this is how we're going to apply it to calculus as we go forward. The slope of a line at a certain point is actually called a derivative. We will learn about those in a couple of months. if that, maybe sooner. So the fun thing about the exponential value is if you pick a point, at any point, the slope of e to the x, so y equals e to the x, equals that value. So at 0, 1, the slope is 1. At 1e, the slope is e. That's fun. And then on the other hand, we are also going to learn how to calculate the area under a curve, which are called integrals later in this course. And the fun thing about e to the x is the area under this curve is just like e to the x, whatever that x value is. And this is just a really nice number, really nice function to use in calculus, so we're going to keep talking about it. All right. We're going to talk vocab, and then that'll be the end of this video. So we've talked about all this already, or I have. The number e is the value that 1 plus 1 over n to the n approaches as n becomes very large. Looks familiar, looks like compound interest. I'm not going to draw a picture. The picture is above in the page above. Natural log. This is ln of x. On your calculator, it looks like that ln key. You might have to push second to get it. Natural log of x. This is like log of x, but it has base e instead of any base. So it's like natural log of e. So it's like base e. All right. So natural log of x equals c means e to the c equals x. This looks familiar. It's just like logarithms that we learned earlier. And the exponential growth is p equals p sub 0, the initial value, times e to the kt, where k is the continuous rate. And then exponential decay is, you've got a negative k here. So this is a positive k value. This is a negative rate value, negative rate, negative k. Remember, exponential growth will look like this. Exponential decay looks like that. All right, that's it for this video. So email me if you have any questions about the history of the number e or any questions over any of these vocabulary terms.